Hello everyone, welcome to the fourth lecture on machine learning with financial applications. So in this class, we're going to talk about a very important topic, which is regularization and also generalization in deep learning or machine learning in general, right? So let's look at the context. So remember that we learned about linear regression. See, this is the two-dimensional data points where our data lives in the single input dimension x and single output dimension y, right? So we can plot it on the graph. For example, it could be like base form, right? So this is x and this is y. Assume that we want to fit a linear regression, and it is as simple as y equals to because our prediction, so I will denote this y hat equals to beta 0 plus beta 1x, right? So this form represents a single straight line. So for example, this straight line, right? So this is a model F. Now, of course, this is not a perfect fit because the two underlying relationship denoted by these courses, right? The actual data represents a curve, right? So we need to add sort of some curvature to the model itself. So this curvature could be something like this, right? So this is actually a better model than the previous model, right? So how do we add this curvature here? So this curvature can be added by something called polynomials. Right? So polynomials means we have an actual term that is a polynomial of the original term. In this case, you can say this model can be represented by y hat equals to beta 0. Still, we have the first order polynomial, right? Which means this is to the power of 1, right? So you can just ignore it. And we have another term, which is x squared, right? So this x squared is an additional term, and we can calculate it, right? Just based on our knowledge of x, because we can just square it and treat it as an additional feature, right? So this type of feature engineering is very powerful because it adds up to the model complexity, right? So the model becomes more flexible and more complex. That's why we can build a curve here. Say we have another scenario and we want to continue to push the boundary by adding more polynomial terms. Right? So for example, we want to say beta 0, beta 1, beta 2, and continue beta 3, this is x cubed, etc. Right? So once we add this, then the form of the curve will be more wiggly, right? So it can be like this. And this is a obvious example of overfitting, right? So overfit because we fit the data point too much, right? There's too much sensitivity here, right? So for example, if my x point is this one, right? This is my x and my prediction is here. And if I change x to here, then it will move to here. So this is my prediction, and prediction changes a lot, even though my x only changes a little bit, right? So this is called high sensitivity, and this is a typical sign of overfitting. On the contrary, this is called underfit because the model is not complex enough, right? It underfits the data points. So we need to strike a power balance, which is in this case the second model, so that we have a good trade-off between underfits and overfits, right? So we'll talk more about it later. So, so let's see. Look at an example here. So the example is that as we increase the model complexity, right? So this is, for example, we're going to fit the line across the dots here, and this is an example of fifth degree polynomial, right? So we have x up to the fifth degree, and you see that this portion, this region seems to be a good fit, right? However, this region itself seems to be a bit of a overfit. And this is the cost. So Q represents the cost or the loss for the current weight, right? So for current weight. because the loss function itself is a function of the weights we have, the current weights. Now we continue to increase to the 10th degree polynomial. You see the cost drops to very small, right? And the points here are almost being interpolated. So this interpolation means that the curve can perfectly pass through the points, right? So this is called interpolation. And it may not be a good phenomenon because it can easily lead to overfitting, right? So in this case, we are fitting every point perfectly, but this gives rise to the extra hump in the curve, which is not something we want, right? It's a clear sign of overfitting region. So we continue, right? So this overfitting phenomenon becomes more obvious, right? It's even more extreme, and the cost even smaller, right? So that's something we want to avoid letting the model overfit the data. So essentially, this underfitting, overfitting represents what we call Bias-variance tradeoff, right? So when it is underfitting, right? We see that the bias is very high, right? It underfits means that the model is very simple, right? So we have a simple model, and that leads to a bias very high, and the variance very low, right? So because it's very simple, then it does not change too much once we change the input x, right? So it's not so sensitive because it's just as simple as a straight line. Now, if it's underfitting, it's overfitting. So we have a complex model, right? And this leads to the bias, right? Which is very low because the model is complex and we do not have it can fit the data very well, right? There's no bias. But the variance, the VAR is very high because it could potentially overfit. It could potentially interpolate the data points, then the variance is very high. So meaning we change the input, then the output could be very different. So that's the trade-off here. Essentially, we're trading off bias and the variance, right? So let's draw a sort of graph here, and we put bias here, we put variance here, and this, for example, is bias very low, bias very high, and this is variance very low, variance very high. So this is just a way to graphically understand what is what we mean by trade-off. So let's look at this region. So this region shows that our bias and variance is both very low, right? So meaning, imagine we have a target, right? We have a circle, and we want to hit the middle of the target. So this is our result of hitting the middle point. So we see that what our attempts are very concentrated, right? That means that we have a small variance. So that's a sign of, because it's very concentrated, its focus squeezes towards the center. And also the center of this joints, of this many hits are centered around the true middle point, right? So that means that it has low bias. On the other hand, if both are high, that means that our predictions are very wide, right? So it's very red range. So it's spread across everywhere, and the bias is also very high. Bias is high means that the center is not centered at the middle point. So I need to redraw the graph. So it means that maybe it's here, it's very wide. And if I the center point, maybe it's here, it's very far away from the real center point, right? So that's what I mean by higher bias. So correspondingly, if our bias is high, which is our average prediction is away from the middle point, but the variance is very low, right? So they stay together. It could be like this one. So the center point, which is away from the middle points, which is high bias, but they stick together, which means we have low variance. So the first situation is we have high variance. It's going to be spread across, right? But the bias is very low. So on average, we still hit the target. On average, we still perform very good. It's just that single times, each time we have high variance. So it can go up and down, right? So this is a typical 4 scenarios of the Bias and the variance trade-off. So let's look at the trade-off more from another perspective. So previously, what we did is that where we actually vary the model complexity. So the model complexity can be represented by the number of features, right? We use in the model. So the more features we have, then the more complex the model will be. So initially we have only one feature, and maybe this is 10 features. So as we increase the number of features, the model will become more complex. This represents the empirical risk. So this is a notion that measures how high or how low our loss is, right? So our loss on the training set. So previously we mentioned mean square error and binary coarse entropy loss, right? So this for logistic regression, this is for linear regression, and all of them are a measure of the empirical risk, and we want to minimize it, right? So this is something we want to minimize, such as we have a good model. So of course you see that this curve represents the training curve, meaning as we increase the number of features, the model become complex. And for each model, for example, if we take, maybe this is 5, if we take 5 features, and the model can minimize the empirical risk to this level, right? So this is what we get. Now increase the number of features and more complex models, then it can do better than the previous model because it's more complex, and this is reflected as a lower empirical risk. So this will continue to decrease, right? So in other words, as we increase the model complexity, the performance on the training set will almost always increase, right? So better performance means a lower risk. So that's what we see for the training curve, right? So this is on the training data, to the point that we have a 0 training error. So this is where we see the model perfectly interpolates the training data, right? So this is called perfect interpolation. Okay, so there's another curve, and we mentioned that we also need the real performance should be coming from the test set, right? So this is the test data, and this train, this is a test. So so the test set performance is more interesting, right? So on the left region, as we increase the model complexity, we see the good progress on the test set because we're learning something, right? But once we pass this threshold, the learning is going to the overfitting region. So this overfitting region, initially we were underfitting, right? So because the model becomes more complex, we're trying to overfit. So overfit is represented by low bias, right? We can hit targets on average very good, but it's high variance. High variance meaning the data changes, then the model is very sensitive. So before we have high bias and low variance, right? So that's the trade-off here. So trade-off means that either we are trade-off between these two regions, right? These two regions, and obviously the best choice is the model that gives me the lowest test set error, right? Lowest. So this is the typical U-shaped curve that describes the trade-off between underfitting and overfitting, or bias and variance, right? So this is what's the traditional view on the Bias and the Bias-variance trade-off, and it is something we will encounter in almost every learning problem, and we want to achieve a good trade-off between bias and variance by getting a model that hits the so-called sweet spot, right, of the U-shaped curve. Okay, so just like I mentioned, this is a traditional view, right? This is a traditional view. Now, in the era of deep learning, right, neural networks, things become a bit more interesting and a bit more complex. So what it means is that assume we still have the curve. This is model complexity, right? This is the model complexity. And this is again our empirical risk, just say risk, right? Which is that's another name for the training set error. As we increase the model complexity, we still see the training performance, right, gets better and until the perfect interpolation point, right? So this means that the model interpolates data. But you see that this is not the end point, right? We still continue to increase the model complexity and see what the performance on test sets it looks like. So typically our model stop here, right? So this is our sweet spots, and this is a U-shaped curve, right? So before it's underfitting, after the sweet spots is overfitting. So we're looking at these points, which is here, right? So now what happens if we continue to increase the model complexity, right? So let it learn itself. It turns out that something interesting happens. So we see that the curve starts to decrease, right? Decrease. So so that's interesting. That means that even if this interpolates, which is fine, right? We just let the model continue to train so that it's more complex. And so this is called the double descent. We have first descent and we have second descent, right? This is double descent phenomenon, which is not something that can be explained yet, right? So machine learning or deep learning specifically is a very active research area, right? People found this phenomenon, but we have not come up with theoretical reasoning on why this is the case, right? So this is very interesting. And just to mention that this model complexity is also a very general notion, right? So it may not represent, so it can be indicated by the number of features, and it also can be indicated by the number of training epochs. Right? Epoch is just how many times I pass through the whole data set. So meaning in the context of deep learning, as long as I train the model long enough, right? Long enough meaning I pass the whole data set to the model many times, right? As long as I continue to train the model without necessarily increase the number of features, right? I just continue to train. So something miraculous happens, right? So as long as the model is being trained long enough, right? So and then this is what we have to see. So at this point, it's even lower risk on the test sets than the previous points, right? So that's something very interesting. And this is exactly what's happening for large language models like ChatGPT, right? ChatGPT. So it is a very big model, right? It has billions of parameters, and it is still a deep learning model, and it's been trained. So initially the performance is not very good, but then they continue to train, and suddenly, so this is the miraculous point. Suddenly the seeds becomes to go better, right? And then become better. That it is like a model, and maybe at this point, this is the model that we're using, and this point comes because we continue to train the model long enough, and it is able to learn the generative patterns. So it is a generative model, and it is able to reason among multiple subjects, right? So this is something we have not yet been able to explain, and it only comes if we train the model long enough, so that it is able to learn these special abilities, right? So that's very interesting phenomenon we're seeing. All right, so now of course overfitting is something we need to address, right? So even if the model in this region is obviously overfitting, but then this is what we see, but this is only particular to a specific training scenarios, right? But in general, we need to address overfitting. So to address overfitting, there are different ways to do that. So let me just say, okay, so we talked previously about the whole model training process. So we have data, right? We start from data, which is X and Y, and we pass it to the model, right? So the model is F. We parameterize it by W, which is our weights. So the data goes to the model, we have predictions, y hat, right? And based on the true label and predictions, we have the cost function, loss, or just noted loss. Okay, so this is loss function. So this is another component. And so we want to minimize the loss by adjusting the model, right? So this is optimization. So this is what optimization does. It adjusts the W key optimization. So this data, model, cost, and the optimization are exactly the 4 components that we can touch upon, right? We can tweak. So by tweaking these 4 components, then we can introduce the form of regularization. So this regularization is something that it is a very general term, right? So this regularization means that we are going to introduce a form of a bias, right, or called inductive bias, so that the model has a better performance on the test set, right? So we can do this via data, via model, via loss function, via optimization procedure, and all these are a form of regularization. We want the model to be regularized so that it generalizes to the test set, right? It does very well on the test set. So I'm not going to go deep, but I have a book that talks explicitly about how this can be done. So I'm just going to talk a bit about the general approach that can be done for deep learning model. So this is the book I'm still in progress of pushing to production. It's called Regularization, Deep Learning, and let's just go through the contents. So potentially, we can do regularization via data, via model, via the objective function, which is our cost function, and optimization, right? So in the book, I also talk about the previous view, classical view, right, on the U-shaped curve, and the modern view on the double descent. So plus the gentle introduction on the regularization, what it is, and also the fundamentals of training deep neural networks. So this is just book still in development, and there are other interesting topics as well. For example, how do we regularize via the so-called smarts, predict, then optimize? So all these are exciting topics, and it is an active area of research. So so yes, if you're interested, then hopefully can take a look as well. All right. Let me just continue with by introducing one specific form, which is to regularization, which is to minimize by minimizing the introducing penalty. Right? So the motivating example is that we have the cost. For example, in linear regression, we have y and y hat, and we're going to take the let me just write it in this form. So we're going to square it, and then sum, and then divide by 1 over. So this is what we call empirical loss, right? But beyond that, we're going to add an additional term called penalty. So this penalty can be in the form of L1 norm. Right? So this is L1 norm. If we write it down, this can be beta 1, right? Beta 2. I'm just going to take the absolute value and of the coefficients, the betas, and then add together. Maybe there's a K of that, right? So this is one to write. So alternative, I can write this as a sum I to K beta I, right? So this is sum of all the betas, and alternatively, I can write this all the beta. Just take the L1 norm, right? This is the L1 norm. So this is what we mean by the L1 norm. It's just so all these are equivalent, right? So this beta should be typically are bolded. So this represents a vector of all the little betas. All right, and we usually add an additional penalty weight, right? This is a hyperparameter called alpha. So again, you see that we want to minimize the loss, right? The empirical loss, but also we want to we do not want the betas to be very big, right? So this is to say the sum of the absolute values needs to be controlled, And this alpha means that we need to sort of balance between what we are doing on the test set in terms of fitting the data, and also in terms of the model complexity. So this beta represents the model complexity. Right? So if the certain beta, for example, beta 2 is very big, right, that means the model is very complex. So we do not want single beta to be very big. That's why we are minimizing the sum of their absolute values as well, right? So it turns out this is a very useful way to control the model complexity such that it is regularized, and it also introduced the so-called sparse estimation. So this is called lasso. This is typically what we know as lasso, or it's also called IO1 regularization, right? So it's using the L1 norm, and it can lead to a sparse solution. So what do we mean by sparse solution? So sum of this beta 2, for example, will be 0, right? Because we by setting this form, then the results of the whole model is that sum of these betas will be 0, right? So then we have a sparse solution. So this is preferred in many contexts, right? So for example, you have a model and you have a lot of features, but you want a sparse set of features that you can use to better interpret, right? And also better understand what are the driving factors. If you have 1,000 features, then you cannot do the interpretation because it's too complex. But if you only have 10 features, then this is something you can do. There's another closed derivation form, which actually comes before the lasso, which is called reach, right? So reach penalty is taking the L2 norm and to square it. What this means is that we're going to take every individual betas, right, and then add together. So first we square them, add together, and then we're going to take the square root, right? So this is the form of the L2 norm. Because we square it, then this is squared, then end of the day it's just the squares added together, right? So this is what we call the reach regression. We introduce a reach penalty. All right. So choosing alpha is something we need to some decision, right? So this is what we call hyperparameter. So when we say it is hyperparameter, it is a parameter that is not optimized by the model. It is a manual decision. So we need to, this is manual. Right? We need to choose the alpha manually before the model training starts. Right. So we need to fix alpha before the model training starts. So the question is, what kind of alpha we need to choose so that it is a decent choice. It is good trade-off, right? To balance the Bias and variance trade-off. So this is the loss, original loss, right? And plus alpha times the penalty on the weights and the parameters, and this is total cost function. So our cost function is consists of the loss and the penalty, and then when we try to minimize the loss, we are implicitly increasing reducing the bias because it's more predictive, but increasing the variance. So this is control the variance. So it's a Bias trade-off. This alpha controls their trade-off. How do we choose alpha here? A typical choice is that we have a data set, and then we divide it into, previously talked about divide it into training and test. But in this we're going to say we're going to do something different. So we have training, we have validation, and we have test, right? So this is used for training the model, and this is for test the model, right? So so we have training and validation. So now the choice of what goes into training and what's going into validation can be varied. So why do we need to have the validation in the first place? Validation is used as a data set to validate the model, right? To see how good the model is. It is used to approximate the test data, right? So test data is in the real world, which we do not know yet, but we know the validation. So we train a model, right? Train a model from F, and then use the model to test on the validation sets and go in cycles. But this choice is a bit subjective. So we can so next round we can just say I want to choose this goes to validation and this goes to training. There's another way to do it, right? So this choice of this threshold, separate threshold is subjective. And a good way is to do this systematically, right? Say, for example, I divide the data into threefold, right? So this is threefold. Coarse validation. So which means that I have 1, 2, 3. This is all my training data. This is all from the training data. Right? So three folds. Now the first round I use 1 and 2 as my data set to train the model, and then validation I use data set 3, right? The default 3. The second time I use 1 and 3 as the training, and then 2 is the test, the validation. And then finally 2 and 3 as the training, and 1 as the validation set. So I have a model, the first model, I have 1 model, I have 2 model, and this is the third model. So different design of test and training sets gives me different models, right? And all these are based on a specific choice of alpha. So the first I choose alpha, and then I divide it into three folds that have 3 different designs, right? And then all these 3 gives me the different models, and I have 3 models. So these 3 models have 3 losses. So L1, L2, and L3, right? 3 losses. And then I would aggregate that. So this take an average, so average loss. So this is average loss, right? This gives me the loss that's not subject to the design of the training data test data or validation data set, right? So this average loss that is most objective, right? Most so the average across different designs of the data, and this average loss measures the performance of this particular alpha, right? And we can say different hours alpha here. So maybe alpha, this is average loss equals to 1, this is 0.5, 2, 0.3, etc. Right? And by building this table, we can find the alpha. Maybe this is alpha 2. That gives us the lowest average loss. Then we can fix this alpha here. So alpha 2, and then plug in the original problem and fix the alpha equals to 2, then continue with the training. So this is what we call by the name of coarse validation, right? Coarse validation to choose the hyperparameter. Right? This is all about how to choose hyperparameter. And later in the later course of this we'll have a session. We have a class, right? A class on how to do hyperparameter optimization, and there's one way to do it, which is called Bayesian optimization. So let me just type it out. Theory and practice. So this is another book I have, which is specifically touched upon the hyperparameter tuning. So this is a problem of hyperparameter tuning, and Bayesian optimization is one way to do it more systematically, right, than the coarse validation. So we can still do coarse validation, but Bayesian optimization is more smart, more principle based. All right, so we're going to touch a bit upon, but you're free to explore this topic as well. Okay, so lastly, let me talk about another way, which is something we do as well, so which is to weight the loss function. Remember that for a particular instance of data, we have yi and we have y hat, the prediction. And we just take the square, and then this is just one instance. We have multiple instances, we add them together and take the average. So it turns out we are treating every error the same, right? So we can introduce so-called weight, right, wi, so that each instance, the resulting impact to the total loss function is different. So this is controlled by the additional parameter weight. So this is another parameter that we need to choose, or maybe defined automatically by the model in some form, right? So this is called weighted least square, right? So weighted least square. This is nothing more than introducing another parameter weight in the form of the loss function. So again, changing the loss function so that it has a sort of bias, right, inductive bias, so that the model performs well, is very common. Right, this is a typical trick, and it is also an active area of research. All right, so that's it about this class and this video. So thanks for watching, and I hope to see you again.